Hi, this video is about writing for thinking, how to write solutions to strengthen mastery of physics. This video is going to take a look at the questions, such as the ones in B Part 1 and B Part 2, on the scan on the screen. These are what I call calculation questions, where typically you are expected to calculate a certain value, write your working, and input your answer into the space, and you'll be awarded the appropriate mark. So these are the questions we'll be looking at. And calculation questions, if you look around your exam papers, they tend to take up about 60% of marks in paper 2 and paper 3. Therefore, they do take up the lion's share of the marks in these papers, and thus it would be an asset to us to have a constructive, clear way to write our solutions to get us as much marks as possible. It will also be good for us to train ourselves to write in a disciplined manner. So what does mastery look like? We want to achieve a kind of thinking mastery that allows us to score well and do well in the exams. And how is it developed? So if you look at the model of the mind on the right-hand side that achieves a high level of mastery, the mind first begins with principles and skills. Then it emanates into a progression of easy to medium to difficult problems. Right? So there's this foundation of principles and skills, and then a progression through increasingly difficult problems. Now, what is hoped is that all these experiences and learning are recorded in the mind in a constructive and linked manner so that it enables us to solve problems well. Principles and skills comprise of the following. So for principles, we have all the laws and concepts in physics. For instance, we have Newton's laws of motion, principle of conservation of energy, laws of thermodynamics, laws of electromagnetism, and so on and so forth. You learn several of them in every chapter. Skills, on the other hand, tend to look at mathematical skills such as solving simultaneous equations, applying calculus like differentiation and integration, graph drawing, and then in the case of qualitative responses, writing explanations well. And then we have easy, medium, and difficult problems. Now, there's a progression, and I like to think of this progression through increasingly complex problem types of the same basic problem. Now, one type of problem I like to make mention to is the slope problem. It's a very basic version of this is where an object is sliding down a frictionless slope. So there's no friction. It only experiences its weight and the normal contact force due to the slope. And typically in such a question, we might be asked to find the acceleration of the object. But this problem can be made more complex, and then it goes up to a medium level and then a difficult level, and you can proceed from there. So for example, at the medium level, we might introduce some friction that's acting up along the slope, such as the diagram on the left. In the center diagram, we might have a string, and that would introduce tension acting on the object. Or maybe a motor is pulling the object up the slope. And then each of these, we could be asked different questions. For example, in the friction scenario, we could be asked again for the acceleration. In the center scenario, we might be asked for the tension. In the right scenario with the motor, we might be asked about the power output of the motor, or maybe even its efficiency. Then difficult versions of this problem might combine it with other problem types. Another problem type you might encounter are pulley problems. And I could combine a slope problem with a pulley problem, and then again maybe be asked for the acceleration of both bodies. Alternatively, we might have an object sliding around in the inside of a funnel. Still a slope problem, because again we have that normal contact force and weight on an inclined platform. But this object is now moving in a horizontal circle, and then we're asked to analyze this problem. So you can see that there's this progression through easy, medium, and difficult problems. How does this serve us? Well, we want our mind to be trained to refer to principles and skills, and then of course the versions of the problem types that we have encountered in a linked manner, recall these links and apply them to the problem that we are seeing in the exam. and this would, of course, maximize our ability to solve the problem. So problem solving is not based on principles alone, and problem solving is not based on experience alone. It is being able to apply them in a linked, cohesive manner to solve it. I would like to contrast this to poor mastery. Now, when a person has not mastered the topic in the way that I have described, one particular case might be the kind of student who have memorized their principles very well, but have not gone through the practice, so they do not carry with them the experience of practice, and so they are unable to solve the problem just with principles because they are inexperienced in applying them. But another more common type is the following, where students enter into the exam and they have done mountains of practice, but the practice is not linked and consolidated towards the principles and skills. And so what they're carrying is, in their memory, is a large number of disparate problems which are not connected to each other. They're fading in and out of memory and thus are nearly impossible to recall correctly and constructively to solve the problem that's facing them. So how can we strengthen mastery? How can we achieve the kind of linkages and memories that we want to have when we solve problems? Well, you can see that, again, that's the animation of how we think. And I would like to bring your attention and make you think about how we write. Now, nonetheless, it's needless to say that the way we think affects the way that we write. Okay? But in addition to that, I would like to persuade you that how we write reinforces the way that we think. So if we were to write in a very haphazard manner, if we are trying to write as little as possible, I think what that entails is that our thinking is very haphazard, our thinking is very minimal. So what I would like to propose is that we adopt the habit of writing in a disciplined manner so as to train our minds to think in a constructive and disciplined manner as well. What we want at the end of the day is to adopt good writing habits that would reinforce our mastery and help us become experts in applying and solving physics problems faster and more reliably. What are the steps that I would like my students to adopt to writing good solutions? Here are 4. The 4 steps are: curate the information of the problem, write down the principle, contextualize the principle, and finally, solve the problem. Let's apply these steps. Here is a typical physics problem. A package of mass 4 kilograms falls from rest from a window from a height of 30 meters. It loses 300 joules of energy due to air resistance. Calculate the velocity of the package upon reaching the ground. Very typical question. I'm sure many of you can solve this. How it looks is like this. What I want my students to do is to draw a diagram. And so you can see U equals to 0, H equals to 30 meters, E lost air equals to 300 joules. So your U equals to 0, by the way, means that the initial velocity is 0 since it falls from rest. Mass M equals to 4 kilograms, height H equals to 30 meters, energy loss, E lost air equals to 300 joules, and initial velocity U equals to 0 meters per second. This is where the students curate and collect the information of the question. And then when we start to solve, we invoke the principle that we want to solve. In this case, a student might use the principle of conservation of energy. Sum of energy initial equals sum of energy final. All right, and this is the raw form of the principle of conservation of energy. Then the student contextualizes it, and now we are looking at the problem, looking at the energies which are relevant to solving the problem, such as gravitational potential energy initial plus kinetic energy initial equals to gravitational potential energy final equals to kinetic energy final plus the energy loss due to air. Thereafter, the student starts to do their substitutions, starts to manipulate the values so that V becomes a subject, and they solve for the final value of 20.9 meters per second. And then here we get the full credit for the answer. Let's break down what the student has written into the 4 steps. So once again, the first step is to curate the information. The second step is to write the principle in its raw form. The third step is to contextualize the principle, where the principle is being rewritten in the context of the problem and looking at, in this case, the relevant energies. And then finally, to solve the problem, and at this point, actually, I would say that it's just automatic application and substitution of values and using mathematics. I always like to say that actually at step 3, if done correctly, the problem is already solved. Let's take a deeper look at each step. Now, when we curate the information, such as writing out all these values, what it does for us is, number one, we collect the important values, so we don't have to keep scanning up and down, looking back at the question to see, what the values were. If we don't do this, then we run the risk of missing important information or wasting time trying to find the information that we thought we saw. This also allows us to define our symbols and subscripts, for example, M and H being the mass and height respectively, and also subscripts. So I like to employ subscripts a lot, especially when there are different forms, different values of the same quantities. For example, there are multiple masses or there are multiple energies. So I use subscripts to identify them. In this case, subscripts have been applied to the energy loss due to air. It allows me to set my units. It didn't happen here, but sometimes questions throw us a bit of a curveball by giving us the mass in grams or giving us a distance in centimeters. And we have to be prudent about it and maybe convert it to the base SI units of meters and kilograms so that we do not make unit errors. And then, of course, we draw a diagram for clarity. If you notice, the question was purely in English, it was just words. And so having a diagram adds clarity and reduces the chances of us making errors and misunderstanding what it is we are trying to do here. Other benefits would be, for example, if we were to be dealing with forces and vectors and forces, vectors, acceleration and that type of values, we can set our sign convention. Now, for step 2, we write up the principle in its raw form. So in this case, the principle is by the principle of conservation of energy. And then in equation form, the sum of energy initial equals the sum of energy final. Now, notice that this is not contextualized at all. It really is the raw form of the principle of conservation of energy. And this starts us off in this mastery mindset from beginning with the principles. Okay, and what this allows us to do is that once we are very accustomed to starting off with raw principles, then many problems start to look alike, especially when they employ the same principle. And that's how we groom our mastery. You can give me very different looking problems, but I see a common thread running through all of them because they all use the same principles and maybe use the same skills as well. Thereafter, we contextualize the principle. Okay, and GP initial plus KE initial equals to GP final plus KE final plus energy loss due to air. And depending on how proficient you are at applying the principle of conservation of energy, you might find this easy, medium, difficult. Let's just for now park it as a medium application due to the number of different types of energy. And so you can see that when you think like this, a student might have been able to recall past questions associated with falling objects and fluids. Maybe in the past they solved a problem of a rock falling in water, or maybe they dealt with a parachutist falling in air. And the experience with that, coupled with the link to the principle of conservation of energy, vastly increases the likelihood that the student will be able to solve this problem well. Furthermore, if they were to write it like this, where they start off with principles and then go on to contextualizing and they have this habit, then the next time that they see similar problems, again, if they see another problem of an object falling in air, like a balloon falling in air or a bird diving to catch a fish, then they stand a much higher chance because they see the common thread, and the common thread being the principle of conservation of energy and the manner in which it was contextualized. Thereafter, the student goes into solving a problem, but by then, the bulk of the thinking has already been done. And like I always say, the question has already been solved. at the step where the principle was contextualized properly. I would like to just raise a bad habit that I observe in many, many students, and I think it does not promote a masterful thinking at all. So looking at the exact same problem, I often see students writing like this. It's just a string of numbers, and then they get the correct final answer. Now, the issue here that reinforces this bad habit is that if you write this, you can get full credit. No problem. You wrote the correct numbers in the correct places, and you got the correct final value. However, there is the failure to list out the principle. And the write out the principle in its raw form. The student fails to do this and fails to contextualize the principle as well. So the links are not reinforced in the writing. And so this really causes a student to end up being like this, where they don't have the links between the problems, and all the problems are just disparate solutions. And so what they're doing is, hopefully if they see a similar problem in the exam, they can roughly remember the order of the numbers and the way that it was written, which I personally do not think is a robust way to go about gaining mastery in solving physics problems. So I really, really encourage all my students, upon solving, to write the principles in its raw form. So this is how, again, a complete solution looks like. And I hope that my students can, again, apply all 4 steps. Some final notes about this work. Good writing also helps with remembering what you are doing when revisiting your work. You can revisit your work after many months when you're going back to look at your tutorials again and you're trying to recall what is it you are doing. And if you don't write them well, then it'll be nearly impossible for you to remember it. But if they were well written, then revising becomes much smoother for your previous work. In addition, during the exam, if you have extra time, you'll also be going back and revisiting your work, and you'd be double checking that you got everything down correctly. So if your solutions were well written, you would be able to understand what your approach was and be able to spot errors better, or be able to have greater confidence that you were doing the right thing. Another benefit is it makes troubleshooting and finding errors a lot easier. For example, if you were calculating the velocity of an electron and it exceeds the speed of light, and this is definitely wrong, and you want to try to find out where you went wrong, if your answers are well written and detailed, you'd be able to spot errors much faster. It makes your working a lot more readable for yourself, for anyone reading your script, especially the person marking your script. Now, you want the person marking your script to really and very easily, quickly understand what you are writing. If they are having difficulty deciphering what you are doing, it is very likely that you will lose the mark. But if you make your scripts a joy to read, I assure you, your marker is going to be a lot more, have a much more pleasant experience marking your scripts, and it just puts you in a better standing. Therefore, also, if you do happen to make calculation errors, if your thinking is laid out clearly and your thinking happen to be correct, the odds of you getting partial credit would be a lot higher if your writing is detailed and clear. Finally, I'm sure many of you are thinking, do I really have to write so much? Is it not a waste of time? I don't have much time during exam. In my opinion, good writing does not waste time. It's being stuck that is the main culprit of time wastage. And if you look at the writing habits, it allows you to get started, particularly in the step of curating information, where you don't really know how the problem is solved just yet, but you can move forward and start writing and start gathering information and getting yourself geared up to solve the problem. You don't really need to know how to solve the problem. You just have to get started, and having this structure allows you to do so.